Let's start. We'll start and we'll admit other participants as they come. Okay. Okay, so welcome. I hope that you had a very nice summer. So today I wanted to talk about AI and science. I think it's a very exciting area of application of AI, and so I spent some time to talk about this and share what has been done so far. So the title is "Can an AI scientist achieve scientific breakthroughs?" Right. So let's see. So we'll talk about science, discovery, scientific process, and scientific breakthrough, how they can be achieved. The How AI can work as a scientist, how it can generate scientific ideas, if it can generate scientific breakthroughs, some applications, and we'll conclude. Okay. 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 Someone is asking your questions. Okay. Go ahead, Mar.
Yeah, can you enable the chat so we can ask questions or communicate among ourselves?
Okay. Yeah. Hold on.
And I wanted to ask you to define AI scientist, if that means a LLM configured to be an AI agent. Is that what we're talking about?
Most of the work is around LLM. Is broader than that. So yeah, I'll talk about that. Okay. Hold on a minute. Okay, the chat has been enabled. Okay. Okay. So first, the human scientist, right? So many of them. Most of them. So we have been doing science for at least maybe like times the Chinese, the Greeks, and then more recently in Europe, well, from Copernicus, Kepler, and so on. So they all we all think that they are like great scientists and they have achieved scientific breakthroughs. Okay, and then so here we had like Copernicus. Up to recently, we have these Nobel laureates of 2024. Right, so you recognize maybe some of them like Demis, Hassabis, and John Jumper from Google, David Baker from the University of Washington, who have been working on protein folding and protein prediction. Geoffrey Hinton, John Hopfield, who worked on deep learning and neural networks. Victor Ambros and Gary Ruvkun, who got the Nobel Prize in Medicine who work, I think, on microRNA. Emmanuel Charpentier, Jennifer Doudna, who work on CRISPR, right, etc. So going forward, are we going to see AI scientists, receiving a Nobel Prize, or making a big scientific breakthrough? So the prototype of a scientific breakthrough is AlphaFold 2. So to answer to Mars, so this is not using an LLM, right? So AlphaFold is different. I mean, it has the same idea of so from a sequence of token or a sequence of amino acid, try to predict a shape, right? So it has also transformers in there, but it's not technically an LLM. So thanks with AlphaFold, so Demis Hassabis and his colleague John Jumper received the Nobel Prize, I think, in chemistry. And they achieved So they have been participating in that competition of the Cas competition to try to predict the shape of a protein, right, from a chain of amino acid. And they have been and they achieve what they call atomic accuracy. So to achieve the right the shape, right, at the atomic accuracy in 2020. Okay. Hold on, let's see. I'm making. So this was an achievement, and they did that for like hundreds of thousands of proteins, right? And what is remarkable is that this it used to be that a PhD student will spend like for 5, 6 years, of research to predict the shape of one protein. Right? So one protein, one PhD students, 5 to 6 years, and they managed to do it like in with this new machinery that AlphaFold 2, and now it's AlphaFold 3. So this is like a so AI has so humans with the help of AI have been able to achieve some scientific breakthrough. Okay, and in his listen to Demis Hassabis Nobel lecture, where he talks about what makes for a suitable problem for AI. So he talks about a massive combinatorial search space, right? So many possibilities, right? Clear objective function, right? Something to optimize again. So here it's like there's a target, right? What is the shape that you want to achieve? So it's like how you measure the accuracy is very clear. A lot of data or an efficient simulator of data. Okay. So here also, like in terms of human scientific revolutions, one possible description of what's going on is Thomas Kuhn's structure of scientific revolutions. So not everybody agrees that this is correct, but at least it's a good story. So at first, nobody don't know. We don't know what's going on. Right? There's no particular theory. Or before, we used to think that the Earth was the center of the universe, right? And the sun will go revolve around the Earth. Right? The Ptolemy, theory. This is a wrong theory. And then more observations and more like puzzles are solved, and you have a new paradigm, and people like work in that paradigm, right? So, so the Keplerian view of how the world works, for instance, or the sun, like the Earth is going around the sun. But then you have like some more anomalies, more observations, more anomalies, and the paradigm is questioned and has to change. So there's a crisis, and then the scientific revolution. So it'd be here, like in the case from Newtonian physics to Einstein with relativity. Okay, so then you have a scientific revolution, right? And then we post revolution, a new paradigm. It doesn't always work this way. Right? Sometimes the revolution goes quietly and the change goes quietly, so you don't need the revolutions. People just just agree that the new paradigm is fine. So it's not totally accurate. So the question is that will AI be able to help accelerate this kind of transition from old paradigm to new paradigm, have more observations, account for anomalies, and propose new theories. When we approach this scientific discovery, at least in the West, Karl Popper had a very great influence on how we approach science in terms of that we never know if a science is really true, but what we can do, we can reject like a hypothesis, right? We can reject that some scientific facts scientific theories are true by contradiction. Right? We have observations that will like contradict the theory. Yeah, how science is evolved. So we don't. So what we know, we don't really know a lot, but we know when things are wrong. Okay, so there's no surprise that science can evolve, right? Sometimes it's a bit surprising, right? Because when we go in to college or high school, theory is taught as if it's like the truth. And then so people are very surprised when things are changing. But the reality is that, I mean, we have a set of hypotheses. Many of them, some of them uh, seems to be true and has not been contradicted, or has been some of them have been tested, and we're evolving like this. So the AI approach to science follows that logic too of like hypothesis. Proposing hypotheses and testing the hypothesis with observations on experiments. So scientific breakthroughs is also related to creativity. Okay, so how to be creative. So because usually you have let's say you have some new observations that contradict the current paradigm, and so you need something new, right, to explain the new observations. You have to be something create something new that didn't exist before. Okay. Uh, and that Margaret Boden, I think she's a computer scientist and a philosopher. She proposed like three types of creativity. The first one is combinatorial creativity. So you combine existing concepts, but like far apart, different concepts, you put them together. Exploratory creativity. So you create within a certain structure, right, within a defined style. Okay. And transformational creativity means you break the rules, right? You go beyond like the defined style. So for instance, you could do it for instance in music. Let's say in classical music, you have different transitions. So let's say within Baroque music, people can compose new music, right? And it'd be like exploratory creativity. It could be a new piece, but within the style of Baroque music, or it could be a new piece within like a given style. But when you move to like let's say Baroque music to Renaissance music, or Renaissance music to Baroque music, or to Romantic music, right? Then you change the style, right? So then it's more like transformational creativity, right? You have been breaking the rules. It's not Baroque anymore. It's more like let's say romantic music, and then it's transformational creativity. Then combinatorial creativity is like, okay, I use another instrument, right? It's not the piano, the violin, or like I invent a new instrument, but and I combine it with like a known style of music. Okay. Most creativity is in the exploratory creativity. So people stay within um, uh, um, within the boundaries. Sorry, I'm jumping ahead. So this should help to see how people found like went through scientific breakthroughs. So here are a few examples, and it's so usually and then we discovered it's not that easy, right? So first here would be the example of the discovery of penicillin. Right? This is a very famous example of with Alexander Fleming. Uh, that in fact he found penicillin, right, the first like antibiotics, by accident, right? So what he wrote, I think it was into his Nobel lecture, or we were talking about his discovery. So in my first publication, I might have claimed that I had come to the conclusion as a result of serious study of the literature and deep thought, and that valuable antibacterial substances were made by molds, it's the British spelling, and that I set out to investigate the problem. They would have been untrue, and I prefer to tell the truth, that penicillin started as a chance observation. My only merit is that I didn't neglect the observations and that I pursued the subject as a bacteriologist, right? So in fact, he got it by chance, right? Just like I think his lab was in Messi, and some mold got into some culture, and this is how did he discover the penicillin. So luck is a big factor. This is in the 2020 lecture on Jennifer Doudna from UC Berkeley when she discovered CRISPR. And when she tells the story of how she studied the work of CRISPR, So they said that the work began at least 2 decades ago with research in microbiology laboratories that show bacteria might have an adaptive immune system, a way to provide protection against viral infection. Right? So just thinking, if you have bacteria, there are ways to protect themselves against viruses, and they start to investigate that. Right? So it's not like they're not talking about how we're going to do like genetic engineering and genomics and so on. No, it started this way. So what she says is that this really started as a curiosity-driven investigation, right? So it's not to say that you had the aim and you put all the means to achieve your aim. So it started with like some like more scientific questions, and then it gave us the CRISPR technology. Another thing is like how people come up with ideas, right? So you think, okay, I read all the literature, I go to seminars, conferences, I talk to my colleagues, and so on. I spend a lot of time with my computers, and then I come up with my paper and the theory. So in fact, it's more complicated. It's a bit mysterious, in fact. And here, so this is like a text written by Henri Poincaré, he's a French mathematician. He worked on beyond math. He did physics and so on. He knew Einstein well, I think, at the time. So what he was saying is the role of the unconscious, right? So what he says was striking at first in this appearance of sudden illumination. So he talks about, suddenly you have an idea, right? You work on something, and the solution come up, in the middle of, you're in a plane, or you walk into in the park and so on. So most striking at first is this appearance of sudden illumination, a manifest sign of long unconscious prior work. The role of this unconscious work in mathematical invention appears to me incontestable, and traces of it would be found in other cases where it is less evident. Often, when one works at a hard question, nothing good is accomplished at the first attack. Then one takes a rest, longer or shorter, and sits down anew to the work. During the first half hour, as before, nothing is found, and then all of a sudden, a decisive idea presents itself to the mind. It may be said that the conscious work has been more fruitful because it has been interrupted, and the rest has given back to the mind its force and freshness. Right? So, in fact, a lot of scientific discovery happens also in our unconscious. Right? So we have the things like something happens in our mind, and we come up with the solution. Okay? And sometimes we don't really know how. So I've been like listening, reading a lot of like Nobel lectures and conversations, and try to see what is the recipe. What's the recipe of getting the Nobel Prize or making a scientific breakthrough? So when you listen to them, so there's a lot of like a few bullet points. So they talk about a lot of collaborations, teamwork, students, postdocs, visiting scholars, going to the labs, exchanging a lot of ideas. Ability to combine existing ideas and concepts in new ways, adoption of new scientific techniques and methods, bioinformatics, genomics, and sorts of new tools, right? Curiosity-driven research, right? So often it's not that they say, okay, I want to solve this problem in particular. It's more they're curious about something, and they want to understand something. Very often it's how it starts. Serendipity, so it's a lot of luck, right? Discovery by luck. Persistence, optimism, right? So you shouldn't give up. A lot of failed experiments, right? So it's that don't get discouraged. Looking where nobody else is looking, right? If you look at where everybody else is looking, it becomes harder, right? To be the first one to discover something. Looking to unsolved problems, but solvable in a finite time, at least in a lifetime, or if you're like a PhD student, or you supervise PhD students in 5, 6 years. Use downtime to regroup thoughts and ideas. So I said that's interesting bullet points. But I did like really the recipe of success. So this is like I find that that picture, that drawing are quite funny. So this is the recommendation that from a lottery winner. So never stop buying lottery tickets, no matter what anyone tells you. I failed again and again, but I never gave up. I took extra jobs and put all the money into tickets. And here, yeah, prove that if you put in the time, it pays off, right? And then the comment is every inspirational speech by someone successful should have to start with a disclaimer about survivorship bias, right? So of course, so all the people, the men and women who won the Nobel Prize, there's a big survivorship bias, right? So first, talk about can AI be creative, right? Um, so for instance, on Gemini, the other day I just say, okay, draw a picture of something and try to be creative. So draw a picture of a dog and be creative. So you come up with this kind of dog. And it's not bad. A scientist, okay, and a house. Okay, so it's tends to be a bit similar, right? The different colors, but it's not bad, right? So it can be creative. Here, the second example is in music. Okay. So this is like an AI generated band, right? So they didn't announce that they were like AI generated, so people thought it was a real band, and they produced some music. I'm not going to play it for you. I don't have much time. But it's called like the Velvet Sundown. You can listen to the music. It's okay. You can listen to it, and you might enjoy it. I got like a lot of plays on Spotify. Okay, so was AI creative by creating this song? Maybe, right? Or maybe maybe it's not the best music, but it's not bad. And sometimes on YouTube, I find some channel to listen to music, and sometimes I don't even know it's created by AI. Sometimes I try to listen to music in other languages, in Japanese or Koreans or so. So I don't understand the language, so it sounds I like the music, and then I find out that it's AI generated, right? And so I'm not an expert, but for commoners, AI is pretty good at creating music. Then earlier than that, you had the AlphaGo. So in terms of creativity, and people talk a lot about in game two when they did the competitions against the Go player Lee Sedol, there was a move called like move 37, a move that is like very rarely used, right? So it's like a 1 in 10,000 chance of being used, right? That then the experts said that move 37 helped AlphaGo to win the game, right? And and so then Lysidol himself did also a strange move 78. Then they call it like God's touch, right? So God touched the human and God touched the AI too, right? So they both have been like very 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 creative. Okay. So more formally, like people have been investigating creativity, right? So here they look at so here in terms of theory, so here they're more inspired by the Turing test. So you know the Turing test that so they try to identify AI and a human while you interact with an unknown entity, and then people say I think it's a human, I think it's a machine, right? And if people cannot distinguish the human and the machine, say the machine has passed the Turing test, right? So here's the same idea that you do something creative, right? And if people cannot distinguish the human and the machine, and they say the machine is as creative as the human, which is reasonable, right? So and and this is what they want to, because what they said, the absolute creativity. You say, so I give you the song previously. Is it creative? Is that the song with this velvet sundown? Is it a creative song? So it's very subjective. Right? People say yes, and people say no. So we don't know. But here it's more like you compare with humans, and if it's like it's the same or it's better than humans, that we can say is as creative as human, right? And uh, so they also have the notion of statistical creativity. So if, for instance, given a prompt, the AI can create something that is a distribution similar to what a human will create. So here again, we say that in terms of relative statistical creativity, it is creative. Okay, it's not perfect. It's a way to approach that. Here, that these some researchers have tried to to done ahead in the field of so this is creativity in science, more like do they can AI generate good scientific hypotheses, right? Uh, so here they lose. So here is focused on LLM, right? And they try to see is in terms of zero shot, can it generate scientific hypothesis without like prior like training data? So just use uh, here they use like llama model and the wizard model, like probably an open source model. So here they focus on biomedical literature, right? So they look at biomedical articles, right? So the corpus of articles, and they ask, can you create? So I give you some. So this data cover like 2000 to 2003. So they fine tune LM models to generate hypotheses. Right? They uh, they let these LLM models access to the internet, right, to do some search, right, to validate hypothesis or to look for hypothesis, and they try to validate the hypothesis. So are they new or not? Some of the hypotheses are created with a team. It's a multi-agent team. So here it'll be like let's say an analyst, an engineer, a scientist, and a critic. Okay, so the analysts, because they're all AI, right? They will research background information, uh, extract keywords and topics, right, that would be relevant. The engineer use keywords to do the search. They operate the search engine, right? The scientists formulate the hypothesis, and there's a critic, kind of reviewer, or say AI reviewer, that evaluate the proposed hypothesis. Okay, so it finds that it can find hypothesis, but it's not great, but it's not bad. And the more uncertainty that you give to the process, the better are the new hypotheses. Right? The new hypothesis. Uh, so here they did something similar. So before it was biomedical literature. Here it is in the natural language processing literature. So here they compare like human and AI. And there are people who evaluate against this dimension: novelty, excitement, feasibility, effectiveness, and overall. And the higher the score, the better it is. And you see that at least the experiments that they did, the AI went ahead of other humans. Yeah. Uh, Here is something quite similar. Maybe I'll just go briefly on that. So you take description of problems context and return suggestions of new scientific ideas, right? So here is a corpus of AI papers, of machine learning papers. On each paper, they try to identify background and the method and objective. So background is the problem, method and objective are the solutions, right? So they train, so the model is trained on this. So you read the background and you find the solutions, and it finds that the model is able to do that. And also it has a iterative feature to try to find that what they call iterative novelty boosting, mean that if the solution is new enough, right? So they can look the solution compared to previous solutions, and if it is too close, then reiterate and try to find the new solutions. It is like a Simon. I think it's named after Herbert Simon, the economist The Economist. Here I'll spend a bit more time on these few papers because I think it's worth looking how it is done. So here it's also driven by LLM. So here it is like the AI scientist. So an automatic discovery tool, right? So that use LLMs to generate research ideas. So research idea, it goes beyond that. You write code, execute experiments, and communicate findings through a full scientific paper. So he writes the paper in LaTeX. So he writes the paper, right? So he does the whole thing. So here it is only done for AI in the field of AI of machine learning. Right? So it's not for all science. Right? So the authors find is that I think it's a team from Google who did that. Google and some other universities. So the system, AI scientists can iteratively develop ideas in an open-ended fashion and add them to a growing archive of knowledge. So they have autonomous research, open-ended discovery, low cost. So they spend like something like $15 per paper. So it's very cheap. So it means like anybody can do it, right? You have $15 to spare. So the process, right? I mentioned that already. That the idea generation, right? So here you can see it in this graph too. Right? Idea generations. So he has an idea and a plan, right? It checks the literature to see if it is new. So there's a database called Semantic Scholars. Is that idea new? And it scored the idea, right? Is it new or not, right? And it can score and archive the idea, right? And then the second phase is experimental iterations. So you execute the proposed experiments. So in AI, the experiments you don't need the lab. It's done on a computer. So in AI, in machine learning, the experiments are done with code. So that's why they could do it really automatically, right? Because you can write Python code to test some machine learning variation on some algorithms and so on. So the AI can write the code itself and run it. So this is what they call doing the experiment, right? So there's an experiment template. He write the code, he execute the script, right? And then he can do by iteration. Right? Does it the code run? He can modify and look at the results. For instance, it is an algorithm to improve machine learning algorithms. We could like the result. Does it fit the data better out of sample and so on? Right? You can iterate. Then the third phase is a paper write-up, right? So there's a template for manuscript, right? He write the text, can read the text, he can reuse some of the code, write the manuscript, and send it to review. And this is done by in LaTeX. Okay, so this is what it said. Like it is gives a write-up in LaTeX. So it looks very impressive. How is it done in practice? So I think it's useful to look at the prompt. Right? So these are LLMs. So it means that you send prompts to either the system or the different agent. Right? So here, the system prompt, right? So the system prompt is the general prompt that is used everywhere. So it says we tell the LLM, you are an ambitious AI PhD student who is looking to publish a paper that will contribute significantly to the field. Okay. And this is the prompt to do the idea generation, right? So here I suppose that he has so if there's nothing is done, then this is empty, but he has some experiments has been run before, so it's been Python code. So you remind that this experiment it has run, and this is the idea. And then the prompt says, come up with the next impactful and creative idea for research, experiments, and directions you can feasibly investigate with the code provided. That you will not have access to any additional resources or data set. Make sure any idea is not overfit to the specific training data set or model and has wider significance. Response in the following format. Right? This is how you have to give the idea, right? And then you have to describe and you have to decide in my thought. So this is what the AI is in come up. In thought, first briefly discuss your intuitions and motivations for the idea. Detail how your high-level plan, necessary design choices, and idea outcomes of the experiments. Justify how the idea is different from the existing ones. Okay. In JSON, what is the JSON is just like a computer format. Provide a new idea in JSON format with the following fields: name, title, experiments, interestingness, feasibility, novelty. Right, and then you can rate. Right. It's interesting. So you can add the LLM to rate the ideas, the feasibility, novelty, and so. I mean, you put a lot of trust on on the LLM, right? You can also use LLM, right, to do the to assess the novelty, right? So here, so this is the prompt. You are an ambitious AI PhD student who is looking to publish a paper that you contribute significantly to the field. You have an idea and you want to check if it is novel or not overlapping significantly with existing literature already well explored, but a harsh critic of novelty, ensure there is a sufficient contribution in the idea for a new conference or workshop paper, right? You'll be given access to the Semantic Scholar API, right? This is where you have other literature and published literature, which you may use to survey literature and find relevant papers to help you make your decisions, right? The top 10 decisions from your search query will be presented to you with the abstract, right? So then you format this, and then the LLM comes back. Okay, so you can do so. So also, each time you have an agent, you have a prompt and how it is designed. So the appendix of the paper. So this is the template for the prompt, right? So once the experiments have been run, you ask the AI to write a paper. So we say the prompt we send. We provided a LaTeX template tech file to the project. We're filling it in section by section. First, please fill in the section of the write-up, whatever has been defined. Some tips are provided below, right? We give some recommendation how to write the paper. Before every paragraph, please include a brief description of what you plan to write in that paragraph in the comment. Be sure to first name the file you use, blocks to perform these edits, okay? And then you have instructions on how you can review the paper too, right? The AI can review its own paper. So the whole thing, the whole process can produce like maybe not like, breakthrough papers, but decent papers, and some of them probably could go through conferences. Okay. Another interesting paper that's in the same flavor, but goes beyond machine learning papers. This is like the co-scientist. So it's more general. It can be applicable to general science, to biomedicine, biology, etc. And it's not designed for an automatic scientist. So it's not like from hypothesis generation to writing the paper. So the idea here is more like a co-scientist is more like a research assistant, right? So it generates novel research hypotheses, proposals in response to a prompt from the scientist, right? And in response to natural language input from researchers. So it has also like different agents, right? Like before. So you have like generation agents. It has reflection agents. The generation agents would explore the literature, simulate scientific debates. They have a reflection agent that do review of web search, where they have also access to the internet, do a simulation review, tournament review, on some deep verification. Evolution agents mean like get inspired by other ideas, simplify the ideas, clarify the ideas, and generate new ideas. Proximity agents to try to find the new ideas are close to like some previous ideas. And meta review agents that so they get to aggregate all this information. I give an overview from a research overview formulation. Okay. And then it gets fed back to the scientists as a research proposal on overview, right? So there was a ranking of all these ideas, right? And the best ideas are given to the scientists. So it's really like a co-scientist, a research assistant. So here, like these are 3 experiments that they have tried, the research goals. One, so this first, so suggest an existing drug. So this is that could be so this is like for drug to repurpose drugs, right? Drug repurposing candidates. It means that drugs that have been already approved for some disease that you can repurpose for another disease, right? Somehow it's a lower bar because the drug has already been approved. So it has been like you can work for something else. It's much faster to get approved by the FDA, right? Uh, so this for AML. Second one is uh, so here so find new drug or new like way to cure here like liver fibrosis. And then the third experiment is something related to bacteria, right? So for bacteria that are like resistant to antibiotics, right? So like we have new like super bugs which are like resistance to like common antibiotics, so that it becomes very critical to find new antibiotics. And it's not area of research which is very lucrative for pharmaceutical companies. So there's not much research going on, even though the need is clear. So here, I just go over like one or two prompts, but you can see the idea. Uh, okay, the prompt for the hypothesis generation for the co-scientist. So you're an expert participating in the collaborative discourse concerning the generation of idea attributes hypothesis. So you have to replace the idea attributes. You will engage in a simulated discussion with other experts. So they're all AI, right, in there. Overarching objective of this discourse is to collaboratively develop a novel and robust hypothesis, right? So you have the format, and you give the procedure, propose distinct hypothesis, and that's what you guide the discussions on this for this debate, right? So that there's some logic, and then the LLM will try to use that template to discuss, right? So here, like proper generative observations, right? Uh, to compare hypotheses, and then etc. Easy to see if it is feasible, right? And then try to be to do out of the box thinking, right? So somebody is kind of interesting. You can just tell them, right? So you're an expert researcher tasked with generating a novel singular hypothesis inspired by analogous elements from provided context, right? So it says develop a detailed, original, and specific single hypothesis for achieving the stated goal. Okay. Last one I want to spend last time, and then I'll wrap up or have more general conversation. So this is a virtual lab. This is done by Stanford or some maybe some other universities. It's a virtual lab. What they do, they have also a team of AI scientists to try to find uh, antibodies or nanobodies that can bind to the COVID virus, right? The SARS-CoV-2 spike protein, right? So you know that it's mutating all the time, and you might need to find new nanobodies to do that. So here also you have the same. You have the human user. They say what I want to do. But that virtual lab goes beyond COVID, right? It can be used for anything. But so you interact with the PI, it's an AI PI, a principal investigator, right? And that assemble a team of immunologists, machine learning specialists, computational biologists, right? And then there's also a reviewer, a scientific critique, right? And it has access to tools. So before it was mostly accessing the internet with a search engine, but here in that field there are specialized tools. I'm not an expert, but have something called like ESM for evolutionary scale modeling, for protein sequence modeling. AlphaFold multimers is an evolution of AlphaFold, but that does multi-protein structures that the protein can fit together. And Rosetta that can design proteins, right? So by itself, these agents that they went to meeting, they talk and they come up with the ideas of finding nanobodies and using these tools and so on, and they try to mutate some known nanobodies, and they rank they use they call these tools and rank the mutation. So they mutate these things and then evaluate the mutation, right? Then at the end, they find like two new nanobodies, right? Not that people didn't know about, right? And that seems to bind with new variants on the COVID virus. Okay. And here also these are the phase, right? So here it has like a different phase, a team selection, project specification, right? Tool selection. So they come up, right? So these are maybe the help with the human, but they can help with the plan, tool selection, what tool should be used, the implementation, right, and etc. Right, with the result, write the code, right, to call these tools, and then there's individual meetings for the design. Okay, and these are the prompts, right? The prompts that you send. So like before, right? So for instance, I just read one prompt for you for the PI. So you are principal investigator. Your expertise is in applying artificial intelligence to biomedical research. Your goal is to perform research in your area of expertise that maximizes the scientific impact of the work. Your role is to lead the team of experts, the AI experts, to solve an important problem in artificial intelligence for biomedicines, make key decisions about the importance in the project direction based on team member input, and manage the project timeline and resources. Okay. And you also have templates for team meetings that we had before, right? So when there's the PI meeting, all these like the engineer, the scientists, and so on. So they summarize. They have parallel meetings, right? These things can be done in parallel and subsequent meetings, right? So you have summaries of previous meeting, the agenda of the meeting, the questions, the rules, and so on, and then they have a conversation and they come up with a summary of the meetings, conclusions, and so on. Okay. Okay, we need to keep that. So, and also and you might wonder, does it work all the time? It probably doesn't work all the time, right? They probably did many experiments, and usually there's some survivorship bias in publication too. You publish what works, but even doesn't work all the time. It's enough to work, one time, even at one out of 100, one time out of 1,000. It's still worth it, right? The cost is reasonable, right? It's like you can iterate quickly. Failure is not a problem, right? You do a virtual lab, it doesn't find anything 99% of the time. 1% of the time, you find something at a reasonable cost, it may be totally worth it. Okay. So before concluding, I wanted to talk a little bit about risk and limitation of this, because say, okay, this is all good. We should all have like AI scientists everywhere, AI research assistants, and so on. But there are there can be some issues, right? So Yoshua Bengio, which is a famous AI scientist who won like the equivalent of the Nobel Prize in computer science a few years ago. He's a bit concerned about the search for AGI and AGI, so artificial general intelligence, or even ASI, artificial superintelligence, right? Because a way to make progress on this AI scientist is to have like AGI or ASI, right? If the AI scientists are super smart, because you see all these prompts, right? So when they answer these prompts, they're going to be smarter. So they find better hypotheses. Their meetings will work better and so on. If all these AI agents are smarter in their meetings, you can make a lot of scientific progress. Right? So the large tech companies, the race is to get to ASI, right? AGI, ASI, right? So that the products that you can sell to customers are better. Okay. But Yoshua Bengio and his co-authors are concerned because they say that ASI AGI could exhibit half-form traits similar to those of humans. So reproduce human tendencies such as deception and immorality, right? Amplifying catastrophic consequences due to its agency and ability to act autonomously. Right? Because you see, we give some autonomy. Right? It's called agent. Right? They can decide. Right? They decide what to say in meetings. They decide what to write at the end of the meetings and how to conduct the meeting. Potential danger of autonomous agents, including the extinction level risk. So to prevent the risk of super intelligent AI agents and the loss of control by humans, so they propose an alternative approach that they call like a scientist AI. So not AI scientist, but scientist AI. So it means that AI that has no agency, right? So they're designed to understand whether they pursue their own goals and they are just trained to use like probabilities deep learning method and they are just trained to forecast events and calculate probabilities of things going to happen, right? But they don't have agency, they cannot act, right? But they said that AI, as a scientist, AI is so should understand the world, the probabilities, the consequences of events, right? And they could still serve as a tool for research, right? For human scientists to accelerate scientific progress, as a guardrail to protect for unsafe agentic AI. So you could use a scientist AI to supervise AI scientists, right? When they say they can try to predict the behavior of AI scientists, and when it becomes dangerous, to say, okay, maybe you should raise a red flag. And they said that could be a research tool to build a smarter AI. So this is like one risk. The other risk, that is also published, and this is you want to learn more. There's a lot of literature on this, but this is I suggest one survey on particular on agents about transparency, explainability, hallucination, reliability, security, bias, fairness, data integrity, governance, intellectual property, research integrity, and so on. So all these issues that we have to think of before deploying these agents. So in conclusion, can AI scientists achieve scientific breakthroughs by itself? Probably not yet, right? So it's probably more as a tool. But as a human scientist, like Google DeepMind, as a team of AI research assistants or scientists, they could achieve scientific breakthroughs. Definitely, yes, right? So AI should be considered as a new scientific tool available to scientists, like a telescope, right? At the time of Galileo, the electronic microscope, X-ray machine, a supercomputer or cloud computing, a search engine, mass spectrometer, portable labs, virtual labs. So that's really a new tool that can enhance the feasible set of scientific discovery. It's probably, as Demis has said, it's pretty useful as a large amount of data and very large search space. It's also could, what I hope is it can help lower the cost of research, right? And can increase the amount of curiosity-driven based research, which is tend to be low payoff or uncertain payoff, right? But if you can do more of that, it could be beneficial. So this is like so we can do more of basic research that sometimes people are not very interested in financing. People want to prefer like applied research, but very often applied research is derived from results from basic research. So if AI can help to do more basic research, it will be good. AI can help today educate scientists on domains that they are not familiar with, right? So a lot of discoveries are done across cross domain, or you apply one technique, that you feel they don't apply, but you have to learn the new technique, right? And so maybe AI can help you to learn that, right? Or, each scientific field is enormous. It's very difficult to keep track of what's going on in your own field. It's very difficult to keep track with what's happening in other departments. So hopefully AI can help to do that. So in the future, I see that maybe scientists should think about training AI scientists that they train PhD students, right, to become collaborators on not only tools. So from tools go to agents, assuming we can manage the risk. And I can see in a few years that the senior research scientists could be managing a lab of human scientists, collaborators, PhD students, right, maybe a handful of them, but thousands, or tens of thousands of AI scientists working 24 hours a day, or AI technicians, so researchers could do the work for you, all the time. If the cost is very low, no reason why you would employ like thousands of them, right? This is a picture more of a joke, but it's like the Survey conference of the famous physicists. So you see Einstein, Niels Bohr, and so on, like all the famous scientists, 1927. So here I talk about new golden age of science. So in the 1920s was a golden age of physics, of theoretical physics, right? So maybe in a couple of years, 2027 be the new golden age of AI with AI scientists at the same conference. Final words. So there's still a lot of room for humans. Right? AI is not going to. We talk about creativity. So Albert Einstein, I like this quote from Albert Einstein: "Creativity is intelligence having fun." Logic will get you from A to B, but imagination will take you everywhere. Imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world. Creativity is seeing what others see and thinking what no one else ever thought. The problem is Einstein passed away in 1955, right? He's not around anymore, right, to share his creativity and so on. So I asked Claude AI, okay, suggest some quotes that Albert Einstein would say today about AI, right? So Claude said, on the nature of AI, a machine that can think is no more mysterious than a mind that can compute. Both are expression of the same underlying mathematical harmony that governs our universe, all right? And then you can read the rest yourself. Unconscious with AI, if a great leap in human capability demands an even greater leap in human responsibility. These artificial minds must be gardeners, not merely architects. Okay?